to write chemical equations, we need to write correct chemical formulas. We need to include states, and we also need to balance an equation. To balance a chemical equation, we need to follow the law of mass conservation. There are many ways to balance chemical equations. Here I have two examples. One is the trial and error method, and basically you follow some common sense. For instance, reacting hydrogen and oxygen, generating water. Because both hydrogen and oxygen are diatomic molecules, and in the product water, hydrogen and oxygen has a 2-to-1 ratio, and it would be really natural for you to put a 2 here, and therefore you would have a 2 here. And by doing that, you notice that you have a total of 4 hydrogen atoms, right? 2 of the hydrogen molecules, so total 4 hydrogen atoms on the reactant side. And on the product side, 2 water molecule essentially means there are 4 hydrogens and 2 oxygens. And on the reactant side, you also have 2 oxygen atoms. So you can clearly and easily balance this equation by some common sense. You could also try to balance your chemical equation systematically. Okay, there are multiple ways to systematically balancing a chemical equation. Particularly later, we're going to talk about how to balance a redox reaction utilizing oxidation states and so on. For now, I just want to show you some really quick and simple method on systematically balancing a chemical equation. You should start with the most complicated substance, okay, or the element appears in the fewest formulas. In fact, in this case, in the combustion of methane, and the most complicated substance and the element appears in the fewest formula happen to fall into one. I'll explain to you momentarily. So if you look at the reaction, the combustion reaction of methane reacting with oxygen, generating carbon dioxide and water. Among the 4 chemicals, methane is probably the most complicated. It's composed of 1 carbon and 4 hydrogens. Okay. Under that circumstances, if you start with 1 methane molecule and to combust it to generating the carbon dioxide, and because you have 1 carbon in the reactant side, and you should have 1 carbon on the product side, okay? But you have 4 hydrogens in methane, that's the natural gas, right? And then you should have 4 hydrogens in the product side as well. So you put a 2 coefficient over here. And under that circumstances, you may notice that in the product side and the oxygen add up to be 4. So 2 oxygens over here and 2 oxygens over here. There are total 4 oxygen atoms. And on the reactant side, in order to have 4 oxygen atoms, you need to put the coefficient 2 in front of oxygen. So by doing this, you are able to balance the equation for the natural gas combustion reaction. As I mentioned, you could either start with the most complicated substance or start with the element appears in the fewest formulas. In this equation, if you notice that oxygen shows up in three places, okay, among 3 different reagents, and carbon shows up twice, and hydrogen shows up twice. So carbon and hydrogen are the kind of elements that appear in fewer formula. So under that circumstances, again, methane is the molecule contains carbon and hydrogen. So you should start with methane and then keep on moving to balance the equation. Okay, so any questions? And if you don't have further question, I'd like you to try to balance this combustion reaction. This is a reaction between propane, the one we put into the small tank, connect to our barbecue stuff, and a Propane also combusts in oxygen, generating carbon dioxide and water. I'll let you to try first, and then we'll look over it together. One of the very interesting chemical reaction is the precipitation reaction. When you mix colorless sodium iodide with colorless lead nitrate, as you can see on this experiment, and when the two solutions are mixed together, this beautiful yellow precipitate is generated. So what happens is, when you're reacting sodium iodide with lead nitrate, you're generating sodium nitrate, which is a strong electrolyte and water soluble. You're also generating lead iodide, and that is this yellow precipitate. To balance the equation, you put a nitrate, because your lead nitrate has two nitrates here, so you add two coefficients over here first, and then since you have two sodium in product, you're going to add two sodium as the reactant, and now you have two iodine in the reactant, and you also have iodide, this iodine 2 over here. So this equation is balanced this way. And really, what is happening when you mix these two solutions together is the principal species in the solution react, generating the product. So principal species in solution is a very interesting concept, and some of your instructors might like to discuss it, some may not, but it's really nice to know the concept. Okay, so sodium iodide, all sodium salts are water soluble and strong electrolytes, means when sodium iodide dissolving in water, it's completely dissociated into sodium cation and iodine anion. And same with lead nitrate, all the nitrate salts are water soluble and strong electrolytes. So lead nitrate, when it dissolves in water, it's completely dissociated into lead cation and nitrate anion. Therefore, before the reaction starts, the principal species in your solutions are sodium cation, iodide anion, lead cation. Lead has a 2+ charge because nitrate has a minus charge, and 2 nitrate and 1 lead form this ionic compound. And then you have this nitrate. These are your principal species in solution in water. Of course, there's water here because the reaction is happening in AQ, stands for aqueous, means in water solution. Okay, and with the principal species in solution, you would know which reagents would react to giving you that precipitation. And this equation is usually called the molecular equation. You're writing the reagents, the reactants, and the products all in molecular form. And in fact, we know that in your solution, there is no such thing called sodium iodide in the solution. Really, in the solution, you have sodium cation and iodide anion, and lead cation and nitrate anion. So it makes sense to write out your ions, and because that's what's really in the solution. Okay, so we can write sodium cation, iodide anion, lead cation, nitrate anion reacting in solution. Okay, and when they react and they form this sodium nitrate, which is a strong electrolyte, so really you form this sodium cation, nitrate anion, and you also generate lead iodide solid, which is over here. You can't write it in ionic form because it's a solid. Okay, and of course we need to balance the equation. Typically, your coefficients in your complete molecular equation should be carried on: 2 sodium, 2 iodide, and 2 nitrate, 2 sodium, 2 nitrate. Okay, and sometimes you might have to double check, really make sure you double check, make sure you have the smallest whole number coefficients over here. Okay, so this is called the complete ionic equation or total ionic equation. As you may notice that in your complete ionic equation, you see 2 sodium in the reactant side and 2 sodium on the product side. You see 2 nitrate and 2 nitrates, and those could be canceled out. Those are what we often refer to as the spectator ions. Okay, after you cancel them all out, you can write your net ionic equation. Only the reagents that react to generate the product. So basically, 2 iodide reacting with 1 lead cation, generating lead iodide solid. Okay, so that's how you describe an equation in aqueous solution. You could describe a molecular equation. You could write your complete ionic equation. You could remove all your spectator ions, write the net ionic equation. And then you may also notice that in the reaction, really what happens was the cation and anions for the two reactants, they're swapping partners. Okay, so ended up you form this lead iodide product. So this reaction is also referred to as the double displacement reaction or metathesis reaction. We're going to see a lot of examples of metathesis reaction, including precipitation reactions. Mole is one of the most amazing and difficult concept for beginners to study chemistry. In fact, once you know what a mole really means, it's nothing too different from any units. Okay, so for instance, if we have 12 eggs, we can see I have 12 eggs. We could see I have a dozen eggs. If you have 6.022 times 10 to the 23rd, it's a large number. If you have this many of eggs, you can see I actually have 1 mole egg. Okay, so basically what this mole is essentially like a dozen, but it's just a larger number to describe the amount of substance. Okay, so the definition of mole as a unit, it's often written as MOL, abbreviated as MOL. Okay, mole is the amount of a substance that contains the same number of entities as there are atoms in exactly 12 grams of carbon-12. Carbon-12 is the most abundant isotope of carbon. Okay, in 12 grams of carbon-12, and there are 6.022 times 10 to the 23rd carbon-12 atoms with 4 significant figures. Okay, the number could go on, and 6.022 is what we usually refer to. Okay, and this 6.022 is also referred to as the Avogadro's number. Okay, and Avogadro is an Italian physicist and played a very important role in contributing to our understanding of the ideal gas law. And this Avogadro's number, this concept of mole, this unit of mole, is not used in daily life. That's probably the other reason people think it's complicated or difficult, because you don't get to use it a lot. because it's only used to represent a group of very small particles like atoms, molecules, in those microscopic scale. Okay, and if it's very impractical to use this unit in a daily life. For instance, 1 mole of ping pong ball. You guys play table tennis, right? The ping pong ball is a standard size, right? 1 mole of ping pong ball, if you cover it to the surface of the earth, and with 1 mole of them, the thickness of the ping pong ball that you use to cover the earth is about 60 miles, almost 100 kilometers. Okay, depends on which unit you're familiar with. It's a lot, right? And so that's why the concept of mole is used more in chemistry, in science field, not in life. But it's nothing that strange or obscure, okay? And it is also the SI unit, International Standard Unit, to describe the amount of substance. Usually we use N to describe the amount of substance, okay? So that being said, 1 mole of carbon-12 contains 6.022 times 10 to the 23rd carbon-12 atoms. And 1 mole of sodium chloride, table salt, right, also contains 6.022 sodium chloride formula units. Okay, a formula unit means this unit, even though we write 1 sodium, 1 chlorine, eventually describing their 1-to-1 ratio here. Okay, so 1 mole of sodium chloride would contain 6.022 times 10 to the 23rd sodium chloride. Means there's gonna be 6.022.03 sodium atoms. There's gonna be 6.022 times 10 to the 23rd chlorine atoms. Okay, and if we're talking about 1 mole of water, it contains this many water molecules, which include, because water molecule has a formula of H2O, so it includes 6.022 times 10 to the 23rd oxygen atoms, but 2 times 6.022 times 10 to the 23rd of hydrogen atoms, because your water molecule has a H2O formula. Okay, so we're gonna do a lot of practice understanding how to convert mole to gram, to concentration, and to the amount of substances. Eventually you become a pro of mole. The mole is no longer something that's obscure to you. I also want you to know that on October 23rd, okay, 10 to the 23rd, officially starting at 6:02 a.m. is the official starting of the International Mole Day. All right, so mole is such an important concept that we are really celebrating what we know, what we understand about chemistry, utilizing this International Mole Day. Writing electron configuration of elements, we know that we need to follow the off-ball rule. We need to follow the Pauling exclusion principle. We need to follow the Hund's rule. And from what I understand, a lot of people get really confused about the off-ball rule. They really don't know, after filling in 1s orbital, what will be the next orbital, and how are you going to remember that? Okay, let's see a couple of examples. I want to start with the carbon, okay? And carbon is an element, number 6, Okay, so it has 6 valence electron. Those 6 valence electrons are going to first fill in the lowest energy orbital, that 1s orbital. And then there's going to be 2 electrons fill into the 2s orbital, and there's going to be 2 electrons fill into the 2p orbital. Okay, sodium. Sodium is an element number 11. And a electron configuration of a sodium would be 1s2, 2s2, 2p6, and 3s1. Okay, so a total of 11 electrons and 10 are filled into this lower energy shell, and there's 1 filled into the 3s1. And of course, we could simplify it by writing an electron configuration of sodium as in a shortcut way, because it's the inner shell electrons would have exactly same electron configuration as the closest noble gas, and therefore for sodium we could also write it as neon in bracket followed by 3s1. And here comes calcium. Calcium is our number 20 elements, and your electrons will fill into 1s2, 2s2, 2p6, 3s2, 3p6. That's a total of 18 electrons. So there are 2 more electrons need to be filled in. We know that in the third shell, we can have 3d orbital, and in fact in the case of calcium, the electrons are filling, the 2 more electrons are filled into the 4s orbital instead of 3d orbital because of a number of reasons. We're going to talk about that in 30 minutes. Okay, and there's effective nuclear charge, there's the penetration, molecular orbital shape, and so on. So basically what I'm trying to tell you is, because 4s orbital is lower in energy than 3d orbital, so when you try to fill electrons for calcium, you're going to fill into 4s orbital first, until for the later elements, and you are going to start to fill the 3d orbital. Wait a minute, Dr. Zhang, this is confusing. We all know that usually the principal quantum number is how you differentiate different shell. You always fill into shell 1, followed by 2, and 3, and 4. But here, you didn't finish filling shell 3. You already started filling shell 4. How do I remember that? Do I need to have something I need to remember? Well, you don't. Okay? Why? Your periodic table are listing all the elements in the order of which orbital you are going to use to fill the electrons in. In the other word, if you look at your first period, there are 2 electrons because there are 2 elements, because these elements, their electrons are filled into that 1s orbital. When your principal quantum number equals 1, you could only have 1 orbital, that's the 1s orbital. When your principal quantum number equals 2, in the second shell, you may have s orbital or p orbital. Your electrons, the electron of your element will be filled into 2s orbital first, followed by 2p orbital. So that's why you have a total of 8 elements in the second period. In the third period, your electrons will first fill into 3s orbital, followed by 3p orbital. Okay, and 3d orbital is of higher energy, so we're not filling that yet. And the next orbital we're going to fill in would be the 4s orbital, followed by 3d and 4p. So you don't have to remember which orbital is of lower energy, how you're gonna differentiate 4s and 3d. Your periodic table already tells you that. Okay, and the first two columns are the s block, and your electrons, the valence electrons of each of the element is filled into the s orbital, and these are your p block. The valence electrons are filled into your p orbital, and this is your d block, and this is your f block when you fill electrons into the f orbital. So this is like a summary, right? And you could follow this, but you don't have to. You could remember this, you don't have to, because you can always begin here. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and on and on and on. So basically, you should be able to fill the right electron configuration for all 118 elements on the periodic table.